Hello everyone, my name is Earl Bellinger. I'm an astroseismologist currently based at the Stellar Astrophysics Center in Denmark, and soon I'll be moving down to the south of Germany to start working at the Max Planck Institute for Astrophysics. Here's a quick overview of the kind of research that I work on. I'm mainly interested in solar-like oscillators, so the Sun and Sun-like stars as well as red giants. And I'm also interested in classical pulsators like Cepheid and Aurelian variable stars. And the main kinds of questions that I think are interesting are how can we use stellar oscillation data to better understand the theory of stellar evolution, and also how can we use this information to benefit other areas of physics and astrophysics. And to answer these questions, I make extensive use of stellar evolution simulations like those from the MESA stellar evolution code, of which I'm now one of the developers, as well as stellar oscillation codes like gyro and attapulse. I'm also trained as a computer scientist, and I make extensive use of machine learning in my research, based mainly on data from ground and space missions like Kepler, TESS, SONG, and Gaia, and so on. So here's an example of the kind of data that I like to work with. This is 1 week of photometry from the Kepler mission of a solar-like star. Now in the time domain, you can't see very much, but as soon as we switch to the frequency domain, clear astroseismic signal emerges. Each of these peaks corresponds to a unique low-degree mode of oscillation. These are global oscillations of the star that grant insight into the underlying stellar structure. Here you can see frequencies. Characteristic frequencies of the Sun is about 3,000 microhertz, which corresponds to a period of 5 minutes. And what do these oscillations look like? Well, here's a highly exaggerated picture of what a quadrupolar oscillation mode looks like. So these are the L equals 2 modes, the modes with a spherical degree of 2. And modes like these and the other modes grant insights into the internal properties of the stars, which we can then use to infer information about their evolutionary history, their masses, and their ages. So how is this done? Well, one way that I have pioneered is the use of machine learning to infer stellar parameters. And here's how it works. On the left side of this diagram, information about the star comes in. Things like its temperature or astroseismic data or other information you have about the star. And then it's passed through to a large ensemble of learners that have learned the relationship between observation and theoretical parameters using a huge number of theoretical simulations. And then finally on the right side, the information about that star comes out, such as the posterior distribution describing its age, its mass, its composition, and whatever other information you wish to constrain about the star. So how well does it do? So here's a diagram showing this technique being applied to 100 stars, or nearly 100 stars, that have been observed by the Kepler mission. You can see that we get surface gravities to about 0.1% precision. We get radii to about 1.5%, we get masses to 3.5%, and we get ages to about 11%, as well as many other parameters which can be constrained, some better, some worse. So that's fantastic. Well, now what can we do with that information? Well, it turns out that these types of measurements are widely useful throughout astrophysics for a variety of endeavors. So here's just one example. It turns out that in order to constrain the radius of an exoplanet, you need to know the depth of its transit and the radius of its host star, if you wish to use the transit method. Well, to get the radius of a host star, astroseismology is the absolute best way to measure that. And you can see there's a clear relationship between how well you can measure the radius of an exoplanet and the radius of its host star. So astroseismology has been of a great benefit to exoplanetary science. A more exotic application is trying to constrain the variation of the fundamental constants over cosmic time. So in this paper from a couple years ago, we looked at the variation of the gravitational constant over cosmic time. And here you can see how the parameters of a star change based on a variable gravitational constant throughout the Hertzsprung-Russell diagram. And because effective temperatures can only be measured to about 100 Kelvin, it turns out that in the HR diagram, you can't really distinguish stars based on a variable gravitational constant. Well, when you move to astroseismology, it turns out that you can get a great constraint on the time variation of the gravitational constant. So here on the x-axis, you can see the large frequency separation. This is the difference in consecutive radial mode frequencies for a solar-like oscillator. And so that's related to it turns out to be related to the mean density of the star. So if you can measure this quantity, you get the mean density directly. And then on the y-axis, you have the small frequency separation, which is related to the age of the star on the main sequence. Both of these quantities we can measure to better than 1 microhertz precision, which means that anywhere in this diagram, if G varies, we can actually constrain that variation. And so that's exactly what we did. We modeled a star with a variable gravitational constant, and we're able to put constraints on how much the gravitational constant could have varied over the 11 billion years history of this star. Because of course, if the star evolved under stronger or weaker gravity in the past, that would have an effect on its resulting stellar structure, affecting how the star oscillates even today. And so from this investigation, we were able to show that the gravitational constant must not have varied by more than 5 parts in a trillion per year over the last 11 billion years. So those investigations are great applications of stellar evolution theory, but what I'm also interested in is understanding how we can use astroseismology to place constraints on stellar evolution theory and understand whether or not stellar evolution theory is actually correct. Now, it seems likely that it's correct in its broad picture, but in fact, the details of the picture, we can easily see that they're not exactly right. And here's how we can see that. So here are 2 solar-like oscillators observed by the Kepler mission, and these are these are models for these stars. And you can see that the models fit nicely into the 1 sigma error boxes of the classical constraints for these stars. And then on the right, you can see the internal structure that's predicted for these stars by stellar evolution theory. So the question is this the correct internal structure for these stars? And the answer is a clear no. Although the frequencies match the frequencies of the models match the star pretty well, in a qualitative sense, they can reproduce all of the broad characteristics of the frequencies. We can actually see extremely significant deviations between theory and observation, up to about 10 sigma, in fact, which implies that the internal structure of the stars is not exactly right. So if that's not the correct internal structure, then what is? Well, we can use astroseismology to answer this question. Astroseismology is sensitive to the propagation of the sound waves inside of the star, and so it can be used to measure the speed of sound inside of the star more or less independently of these stellar evolution models. So we did that for 16 sig A and B, and here would be the line of no difference. So this is the relative difference in sound speed inside of the star, where this is the center of the star, and this is towards the outer layers. These are the differences in sound speed in this part of the star. And you can see that there's some tension between the internal structure of this star that's predicted by stellar evolution theory and the actual structure of this star. In the case of 16 sig B, the agreement is much better. We also applied this technique to a star that has a small convective core. And here we found that there's a significant gradient in the differences between the internal structure of the best fitting model from stellar evolution theory and the actual structure of the star. We furthermore tried to test the physics of stellar evolution by constructing stellar evolution models with different assumptions about how these stars evolved. In particular, we tested the effect of convective core overshooting, so artificially extending the convective core's size to make a larger core, as well as including the effects of element diffusion into the calculations. But none of these effects that we tried were able to correctly reproduce the structure of the star. And so this represents a mystery or a puzzle. There's apparently missing mixing in the interior of this star, which is not currently being accounted for in stellar evolution theory. So this would be a great thing to resolve. Most recently, we have applied this technique to a subgiant star. So this is a star that's now off the main sequence. It has exhausted its central hydrogen reserve and is now fusing hydrogen in a shell surrounding its core. So its core is nearly pure helium. Its shell is fusing hydrogen, and then it has a radiative envelope. And it turns out, and then beyond that, it has a convective envelope. And it turns out that using astroseismology, we can probe these regions of the star. We can measure the sound speed in the core, and we can measure the sound speed in the hydrogen burning shell. And then we can compare those measurements to the predictions made by stellar evolution theory. And it turns out that in the radiative zone of this star, that stellar evolution models appear to roughly get the answer right. Likewise, in the hydrogen burning shell, the sound speed of the evolutionary models seems to be the same sound speed as in the star. There's greater tension in the core, but it's difficult to say whether or not these are real differences. So broadly speaking, the theory of stellar evolution seems consistent with this picture of subgiant structure. There may be some additional understanding to come in the core, but we will need to apply these techniques to more subgiants in order to understand if there's really missing physics in subgiant evolution. So that's what I wanted to tell you about my research, and if you're interested in that, then please reach out to me and I'd love to collaborate on some projects. Goodbye.